A microscopic bubble could erase the laws of physics. That's the idea of a quantum bubble. It's a real theoretical threat woven into space itself. Our whole universe might be balancing on a knife's edge. A cosmic instability, a random quantum event could trigger it. It would start a wave of new physics, and that wave would expand at the speed of light. Everything we know rests on a foundation of temporary order. It's a haunting possibility to live in a universe that could rewrite its own rules without any warning. For a long time, we thought the universe was a perfect machine, predictable. The physics we knew, the math that got us to the moon, it all pointed to a cosmos with fixed rules. Gravity pulled, light traveled at one speed. The forces were constant like the stars. That was classical physics. It was comforting. It felt like the story was finished. All the laws were set in stone. But that certainty was an illusion, a simplification, and it started to crack. We found the quantum realm, a place buzzing with randomness, probability. Particles could be in two places. They could appear from nothing. This wasn't a machine. It was a probabilistic ocean. And in that discovery, there was a deeper idea. More unsettling, what if the laws themselves weren't the final foundation? What if they were just local rules for our particular corner of existence? Think of a valley, a stable place with its own climate, its own geography. You might think the whole world is like your valley, that its rules are universal. But if you climb to the peak, you see a vast landscape, other mountains, other, deeper valleys, each with its own conditions. Physicists like Hawking and Susskind have suggested our universe is like that. One stable valley. Our laws of physics might not be the only possible laws. They might just be a low-energy state, a comfortable resting place in a cosmic terrain filled with other possibilities. More exotic ones, this state is called metastability, stable for now but not forever. A marble in a shallow dip on a hillside is metastable, it seems still. Until a jolt sends it rolling into a deeper, more stable gorge. Our cosmos could be that marble. Our reality feels permanent, but its foundation might only be temporarily quiet. That's the foundational shift from eternal laws to temporary local conditions. It's the first step. It peels back that layer of cosmic permanence, and it asks a question. If we're in a metastable valley, what lies in the valleys below? So the valley itself, what it's made of, the actual substance. To get at that, you have to stop seeing the universe as a collection of things. You have to see it as fields, a symphony of fields. The vacuum isn't empty. It's not empty at all. It's alive. It hums. According to quantum field theory, the most fundamental layer is a set of invisible fields. They permeate everything. Think of an infinite, invisible ocean. Every point in space, from inside a star to the void between galaxies, is saturated with them. The electron field, the quark field, the electromagnetic field, and crucially, the Higgs field. What we call particles, electrons, photons, quarks, the stuff that makes up you and me and this screen, they aren't little solid balls. Their excitations, localized ripples, vibrations in their respective fields. An electron is just a tiny knot of energy in the vast electron field that changes everything. It means the properties of our universe, the laws themselves, are dictated by the state of these fields, by their energy. Each field has a ground state. Its lowest possible energy configuration. Picture a ball resting at the bottom of a deep, smooth valley. That's a stable ground state. It would take a huge amount of energy to lift it out. But fields can also exist in false vacuum states, metastable states. That's like a ball balanced on the rounded top of a hill, or resting in a shallow dip on a hillside. It looks stable, it feels stable, but it's not at the lowest possible point. A nudge, even a tiny one, could send it rolling down into a much deeper valley far below. Our entire cosmos, every law of physics we rely on, depends on which valley these quantum fields are sitting in. The strength of gravity, the speed of light, the mass of an electron, all of it is determined by the current energy state of these invisible oceans. We exist, and reality works the way it does because for nearly 14 billion years, the fields have remained in their particular, comfortable dip. But that dip may not be the deepest one available, and if that's true, then the stability we take for granted is an illusion, a temporary quiet in an energetic landscape filled with far more stable and far more alien possibilities. The comfortable dip we live in, this valley, might be a trapdoor. That's the false vacuum. It's an unsettling idea in physics. What we see as empty, stable space, it's not the final ground floor. It's a temporary floor, a suspended platform, and our whole universe is built on it. Picture a vast landscape of energy, a terrain of possibilities for how quantum fields can be arranged. Our universe sits in one particular dip in that landscape. It's a local low point. From where we are, it feels like the bottom. Everything is stable here. The laws work, but if you could see the whole cosmic topography, you might notice our dip isn't the deepest one. Far below our valley, there's a much deeper gorge. A state of lower energy, a true vacuum. Our position is the false vacuum. It seems empty and final, but it actually holds latent, pent-up energy, waiting. The analogy is a ball resting in a shallow dent on a steep hillside. It looks still, it feels secure, but it's not at the base of the mountain. The slightest vibration, the smallest nudge from the random quantum world could dislodge it. And once it starts rolling, there's no stopping its fall into the deeper, more stable valley far below. In our universe, the field that might be holding us in this precarious position is the Higgs field. The one that gives particles their mass. Its discovery was a triumph, but it also opened a door to a mystery. The mass of the Higgs boson, the particle that proves the field exists. It's not what many theorists expected. Calculations by physicists like Joseph Licken suggest something strange. The measured value hints that the Higgs field might not be in its true lowest energy state. It might be in a false vacuum, a metastable configuration. Our entire reality, with all its constants and forces, depends on the current value of the Higgs field. If that value represents a false vacuum, then everything we know is built on a foundation that is fundamentally temporary. It's a waiting game, a cosmic arrangement that's lasted nearly 14 billion years. Yet it could, in principle, collapse at any moment, not from an external force but from an internal shift, a random quantum event providing that tiny, fatal nudge. That random nudge has a name: quantum tunneling. It's maybe the strangest idea from quantum physics. In our world, to move a ball from one valley to the next, you need to give it the energy to roll over the hill between them. That's the classical rule, but in the quantum world, particles don't always do that. They don't have to climb, they can just appear on the other side. Like the ball found a tunnel straight through the mountain. It's not magic, it's a basic part of quantum mechanics. It comes from probability. A particle isn't just one point. It's a cloud of possible locations. There's a small chance it can be somewhere classical physics says it shouldn't have the energy to be. That's how radioactive decay happens. A nucleus held by forces that should keep it together forever can suddenly spit out a particle. To us, it just happens. The atom tunnels through a barrier it shouldn't cross. Now take that idea, scale it up, not to an atom, to the whole universe. Think of the Higgs field. It's holding reality in a false vacuum state, like an ocean sitting in a shallow dip on a hillside. Quantum field theory says this field isn't perfectly still. It's always quivering, tiny random fluctuations, virtual particles appearing and vanishing. Most of these cancel out instantly, but quantum mechanics allows for something else. What if somewhere in one tiny region, the field doesn't have a small fluctuation? What if it has a massive one, a random quantum jump so large it doesn't just jiggle in the shallow dip? It tunnels through the energy hill, the hill between our false vacuum and a deeper, true vacuum below. In that one small point, the field would be in a new, lower energy state. It would have tunneled, and that point, that seed of new physical laws, would be the start. The birthplace of a quantum bubble, a microscopic speck of true vacuum suddenly existing in a universe of false vacuum. From then, the rules change. The new state is stable, it's energetically favorable. Nature seeks the lowest energy, so this new state wouldn't stay small. The boundary between the new laws and the old laws, the bubble wall, would start to expand. Driven by a huge release of pent-up energy, it would rush outward at light speed. One random quantum event, a cosmic version of radioactive decay. It could rewrite the manual for everything. And we'd have no way to see it coming. The trigger is a quantum whisper, a random event that could end physics as we know it. So what could that whisper be? What specific process nudges the field to tunnel? The unsettling answer is that several known phenomena might serve as a catalyst. The first candidate is one of the most energetic events in the universe. An ultra-high energy cosmic ray collision. These aren't ordinary particles. They're atomic nuclei, often iron, accelerated to nearly light speed by unknown cosmic engines. When one of these projectiles slams into a particle in our atmosphere or in deep space, the collision concentrates immense energy into a vanishingly small point. It creates a fireball of exotic particles, conditions that, for a fleeting instant, mimic the earliest moments of the Big Bang. In that microscopic maelstrom, the quantum fields are stressed and twisted. Could such an event, a natural particle accelerator of unimaginable power, push the Higgs field just far enough to trigger the tunnel? It's a possibility. It ties our fate to the violent heart of distant galaxies or colliding galaxy clusters. An even more extreme environment exists at the edge of known physics. The singularity of a black hole, gravity becomes infinite there, space-time curvature breaks down entirely, our equations fail. In this realm of pure chaos, the concept of a stable vacuum may have no meaning. Some theoretical models suggest the violent quantum fluctuations near a singularity could be the ultimate pressure cooker, a place where the false vacuum is so stressed that a bubble of true vacuum spontaneously forms. If this happened, the new bubble would be born within the event horizon, hidden from our view until its wall expanded beyond the black hole's grasp. Our universe's doom could incubate unseen. In the darkest prisons of space-time, but perhaps the most haunting possibility requires no spectacular cosmic event at all. The trigger could be utterly mundane. A random quantum fluctuation in empty space, the same kind that creates virtual particles from nothing. In the vastness of the cosmos, over trillions of years, every possible quantum event, no matter how improbable, will eventually happen. A fluctuation large enough to cross the energy barrier is statistically inevitable if the universe lasts long enough. It's a game of probability on a cosmic scale. The dice are always rolling. This means the catalyst might have no cause we could ever point to, no warning flash in the sky, no cataclysmic collision. Just a quiet pop in the void, a quantum roll of the dice that resets the board. Our fate, then, is not written in the stars, it's written in the fundamental randomness that underpins them. It leaves us in a universe where stability is a temporary guest, and the guest could decide to leave at any moment for no reason at all. It happens in a point. A new universe is born. A microscopic region, maybe smaller than an atom, goes through a phase transition. It's like the first ice crystal forming in supercooled water. The water is liquid, but it's unstable. A single crystal appears. Its structure is different, solid. It imposes a new order on the molecules around it. But here, the crystal doesn't just change the state of matter. It changes the rules of matter itself. This is the nucleation of the true vacuum bubble. In that tiny volume, the Higgs field, or maybe another fundamental field, has completed its quantum tunnel. It's settled into a lower energy state, a deeper valley. And in doing that, it instantly rewrites the local laws of physics. Inside the boundary of this new bubble, everything is different. The fundamental constants aren't constant anymore. The speed of light, the strength of gravity, the masses of electrons and quarks, the charge of a proton, these aren't universal truths. They're local conditions, set by the energy of the quantum fields, and those fields have just shifted. So inside, the speed of light might be slower, or faster, or light as we know it might not even exist. Gravity could become repulsive, atoms might be impossible to form. The work of physicists like Sidney Coleman helped us understand this boundary. He called it a domain wall. An infinitely thin, yet impenetrable surface of pure energy. On one side, our universe with all its familiar rules. On the other side, a new universe with a completely different, incompatible set of laws. They're not just different places, they're different logics of existence pressed up against each other. This wall isn't a physical barrier you could touch, it's a front of transformation, a wave of rewriting reality. As it expands, it converts the false vacuum of our old universe into the true vacuum of the new. Anything it passes through isn't destroyed in an explosion. It's simply translated. Its very particles, the forces that hold it together, are instantly recast into new forms. Forms that obey the new regime. A star, a planet, a molecule in the void would cease to be what it was. It would become something else, something governed by a physics we can't predict. This is the conception of a new law, a genesis event, not at the beginning of time but within it, a foreign reality growing from a quantum seed, and it begins to spread. The interior of the bubble is the second great mystery. What would the true vacuum actually look like? We can't know. It's pure speculation, a physics we can't write. Because once the field tunnels, every rule we use to describe reality becomes invalid. Our equations break down. We're left with possibilities drawn from the edges of theory. The first possibility is a barren, cold void. In that scenario, the new vacuum state has a much lower energy, so low that the fundamental forces, the electromagnetic force, the strong nuclear force, they're altered beyond recognition. They might become too weak to bind particles together. Protons and electrons could no longer form atoms. Nuclei would never fuse. The whole dance of chemistry that builds stars and planets and life, that becomes impossible. The interior would be a soup of free particles, non-interacting, drifting in a dark, featureless expanse. A universe where structure is forbidden, but it could be the opposite. A hyper-energetic plasma. The transition from false vacuum to true vacuum releases an immense amount of latent energy. That energy could ignite a firestorm of new particle creation, far more intense than anything we know. The bubble wall would be preceded by a shockwave of radiation, scouring space clean. Inside, temperatures and densities could rival the first moments after the Big Bang. In that cauldron, exotic forms of matter and energy we can't even name might reign for a fleeting instant. It could be a brief, brilliant flash of a new kind of physics before settling into something else entirely. Then there's the most extreme possibility, instant collapse. Some models suggest the true vacuum might not be stable at all, but a gateway, a lower energy so profound that space itself becomes unstable. The geometry of spacetime could curve violently inward. The entire interior of the bubble, no matter how large it grows, might instantly crumple into a singularity. It wouldn't be a black hole from our universe. It would be a knot of non-existence, born from new laws that allow for such a thing. One moment there is space, the next, a mathematical point where all concepts of inside vanish. That's the core of the mystery. The laws inside aren't just different versions of our own. They are entirely alien, unpredictable. There's no reason they would favor complexity or structure, or even the persistence of time as a flowing river. They could be laws where time loops back on itself, where cause and effect are reversed, or where dimensions of space unravel. Our cosmic rulebook isn't just edited in the bubble. It is erased, the page is blank, and what gets written next comes from a logic we cannot comprehend. It leaves a haunting thought. If such a bubble passed through Earth, we wouldn't be annihilated by fire. We would be translated. Every atom in our bodies, every force holding us together, instantaneously recast into something obeying those new alien rules. We would cease to be, not with a bang, but with a silent redefinition of what be means. That law doesn't stay where it starts, it spreads. The bubble wall, the line between the old physics and the new, it begins to move. And it moves fast. There's a colossal energy difference between the false vacuum outside and the true vacuum inside, opening a floodgate. All that pent-up energy releases, and it creates a constant, unstoppable pressure pushing the wall outward. This expansion isn't like a balloon inflating. It's like a crack racing through safety glass. The glass is whole, then a flaw appears. Stress concentrates at the tip, and the crack front zips across the entire sheet in an instant. Transforming its structure, the bubble wall is that crack front, but in the fabric of reality. It's not a physical object moving through space. It's space itself being rewritten, point by point, as the front passes. And the speed of this rewriting is the chilling part. The wall expands at nearly the speed of light, the fastest speed possible. That phrase, nearly the speed of light, it sounds abstract. But translate it. Light takes 100,000 years to cross our Milky Way, 2.5 million years to reach Andromeda, nearly 14 billion years to travel from the edge of the observable universe to us. A bubble born in a distant galaxy could cross those same voids in a comparative blink. There's no outrunning it. No warning system could work. The first signal we'd get that the bubble existed would be the bubble wall itself. And since it moves at light speed, that signal and its consequences arrive simultaneously. You can't see the light from an oncoming tsunami if the wave itself travels at the speed of light. It turns the universe into a silent, dark ocean. A wave of redefinition could be moments away from any shore, and we'd never know until it washed over us. The expansion is relentless, absolute. Every atom, every star, every galaxy in its path isn't destroyed but transformed, translated into the new physics of the interior. The old universe is consumed not by fire but by a change in the fundamental code, the ultimate cosmic reformatting, a wave that doesn't just end worlds but ends the very rules that allowed those worlds to exist. And it would do so with a quiet, unstoppable finality. No room for escape, no time for farewell, just an instantaneous, silent transition into the unknowable. The wall is the final frontier, not a place but an event, an instantaneous line where one set of cosmic rules is swapped for another. You can picture it as a sheet of pure transformation. Thinner than any known particle, but stretching across light years as the bubble grows. That's the domain wall, a topological defect in reality. Topological, that's about shape, the overall structure of the field. When the Higgs field tunnels from its false vacuum to the true vacuum, it doesn't change smoothly. It flips like a cosmic light switch. On one side, the switch is up. That's our physics. On the other side, it's down, the new physics, and the wall is the line where that switch flips, an abrupt change in the ground state of the universe. Inside that thin boundary, the field is caught between two worlds. It's stretched. It holds the energy difference between the old vacuum and the new. The result is a surface of staggering energy density, a concentration of force so extreme it defies understanding. If you could see it approaching, it wouldn't look like a barrier of metal or rock. It would be a shimmering, bright horizon of raw potential, a curtain of energy where the mathematics of existence are being rewritten, and anything from our universe that meets this curtain, its fate is beyond destruction. It undergoes translation. Think of a complex sentence written in English. It has structure, meaning. Now imagine a rule that instantly translates every word into a new, alien language. Different alphabet, different grammar. The sentence ceases to exist as English. Its components are still there. The letters might look similar, but the meaning, the logic that held it together, is gone. It has become something else. That's what happens at the wall. A star isn't vaporized. Its atoms, the quarks and electrons, are processed through this energy sheet. The forces that bind those particles, electromagnetism, the strong force, their properties of the old vacuum state. As the wall passes, those forces are instantly replaced by the new ones from inside the bubble. The particles are recast, given new properties, new masses, new ways of interacting. They become citizens of a new regime. The structure of the star, which depended entirely on the old forces, dissolves. Not into chaos, but into a new order, an order that likely cannot support anything like a star at all. It's a fundamental dissolution and a recreation. The end of our physics isn't an explosion. It's a silent, instantaneous redefinition of every component of reality. From our perspective, it would be the last moment of existence as we know it, followed not by darkness but by a state of being for which we have no words, no concepts, and no possible warning. The moment of contact would be the last moment for our physics. If that bubble wall reached our solar system, it would just be a horizon of light, expanding across the sky at light speed, silent, no sound, no tremor, no warning flash. The first sign would be the atmosphere changing right in front of us, but we wouldn't see it because sight would be one of the first things to go. As the wall passed through the outer atmosphere, the rules would change. The electromagnetic force, rewritten, that force dictates how atoms interact with light. Photons from the sun would stop scattering blue light off the air. The sky wouldn't be blue anymore. It would become something else, transparent or black or glowing with some other light, but that change wouldn't matter. Because the photons hitting your retina would be under the new laws too. The signal they send, the chemistry of vision, it would just stop making sense. Your last visual experience would be a flood of nonsense, then nothing. The transformation would be total and simultaneous. This isn't an explosion moving through the planet. The bubble wall isn't a physical object, it's a redefinition of the quantum fields that fill all of space. When it passes a point, every particle at that point is under a new regime. Inside your body, the strong nuclear force, the force that binds atomic nuclei together, that would be recalculated. It's a precise balance, a delicate tuning that lets protons and neutrons stick. If its strength changes even a little in the new vacuum, nuclei become unstable. They would just fall apart, not with a blast, a quiet dissolution. The atoms in every molecule, in your cells, in the air, in the ground, they would cease to be atoms. They'd disassemble into a soup of elementary particles, quarks, electrons, floating free, but those particles aren't sacred either. Their properties, mass, charge, those are gifts from the old Higgs field. In the new vacuum, those gifts are revoked. An electron might become thousands of times heavier or lose its charge entirely. The quarks in a proton might no longer feel the force that binds them. The very concept of a proton would evaporate. What was a human body, a tree, an ocean, a mountain, would become a cloud of unrecognizable entities, interacting under alien rules. Rules that likely can't form complex structures. There would be no pain, no sensation. The system that processes sensation would have been erased at a level more fundamental than any nerve signal. And Earth is just one point. The same silent translation would happen to the sun as the wall passed through it, the intricate fusion reactor at its core. It depends on the precise strength of the weak nuclear force to turn hydrogen into helium. It would simply stop. The outward pressure of light that holds the star up against gravity would vanish. Because photons themselves are redefined, the sun wouldn't explode. It would just cease to function as a star. Its light would change, then go out, not because it's extinguished. Because the physics of light has been retired. Across the galaxy, across the universe, every structure that depends on our specific set of forces would unravel. Galaxies would dissolve from ordered spirals into formless clouds of transformed particles. The universe as we know it, a place of stars, planets, nebulae, it would be gone. Not destroyed, edited out of existence, replaced by a new cosmos with different and likely barren fundamental rules. It's the ultimate quiet ending. Not with a bang, with a rewrite. But that question goes deeper. Could anything survive? Not just matter, but information, memory. Could a thought or data, or even just an echo of a civilization last when the laws that made it possible are gone? The answer is almost certainly no. It's not just destruction, it's an informational apocalypse. Imagine a library, a vast library with every book ever written. Then imagine a change so fundamental that the idea of ink on paper, of letters making words, becomes meaningless. The library isn't burned, the books are still there. But they're not books anymore, they're just collections of fibers. Their arrangement is random noise now. The stories, the knowledge, the history, it all vanishes. Not because the medium is gone, but because the code to read it has been deleted. That's what the bubble does to the cosmos. Our universe is that library. Stars are sentences written in gravity and fusion. Planets are paragraphs of geology and chemistry. A living brain might be the most complex book of all, a story written in neural connections and electrical signals. All of it needs a very specific, tuned set of physical laws to give it meaning. Change those laws and the narrative dissolves into gibberish. The forces that allow complex chemistry, stable orbits, the storage of information, their local conditions. In the new vacuum, those conditions are revoked. So could a brain or a computer or a stone carving survive? No, their structure is an expression of our physics. When the physics changes, the structure loses its reason for being. The atoms might still exist in some form, but the ordered relationships between them, the memory they hold, would be scrambled into chaos. There are speculations at the very edges of theory, ideas from digital physics or quantum information. They suggest abstract patterns, mathematical truths, might exist independently of any physical instantiation. That consciousness or information could be a pattern that transcends its substrate, but these are speculative, fringe concepts. The overwhelming consensus is bleak. The bubble is a total informational reset. It doesn't just end life, it erases the very possibility of recording that life ever existed. Every fossil, every light beam carrying an image of a dead star, every cosmic microwave background photon whispering of the Big Bang, all of it would be translated into a new, incompatible language. The history of our universe, its 14 billion-year story of expansion and structure and maybe life, would become an unreadable footnote in a new cosmic ledger. That poses the most profound question. If such an erasure is possible, what is the permanence of any achievement, of any identity? We build civilizations. We create art, seek knowledge, send signals into the void, hoping for a legacy. We assume the universe remembers, even if just in the arrangement of atoms. The quantum bubble whispers that this assumption might be the greatest cosmic illusion, that everything we are and everything we've done is written on a chalkboard that could be wiped clean at any moment by a process that doesn't even know we were there. So we're left with this question: how likely is it? We've described this idea of cosmic erasure, but is it something that's definitely going to happen, or is it just a mathematical ghost story? Physicists don't deal in ghost stories, they deal in numbers, so they've tried to calculate the odds, the probability that in a given volume of space over a given amount of time, the quantum fields will tunnel and create that fatal bubble. The equation is complex, full of constants and energy terms, but the core idea is something we can hold onto. It's a game of chance played across the entire cosmos. Think of it this way: imagine a vast, dark room. In that room is a single, special grain of sand. That grain has a microscopic switch. Every second, a random number generator spins. The odds of it landing on the exact sequence that flips the switch are astronomically small. 1 in a number with dozens of zeros. For that one grain in that 1 second, a catastrophe is almost impossible to imagine. Now fill that dark room with sand, not just a pile but an ocean of it stretching farther than you can see, and let that ocean exist not for seconds but for billions of years. Each grain, each second gets its own roll of the dice. Suddenly, the impossible becomes a matter of when, not if. The universe is that ocean. The grains of sand are every cubic centimeter of space. And the dice have been rolling for nearly 14 billion years. This is how physicists frame the risk, the probability per unit volume per unit time. For a single cubic centimeter of space, a volume smaller than a sugar cube, the chance of a bubble forming in any given second is so incredibly tiny it's effectively zero. You could watch that sugar cube of vacuum for trillions of times the current age of the universe and see nothing. But the universe isn't one sugar cube. It's an almost unimaginable number of them. The observable universe contains around 10 to the 85th power cubic centimeters. That's a 1 followed by 85 zeros. An amount that makes every grain of sand on Earth look like a single speck, and it's all rolling the dice all the time. When researchers like Joseph Licken or Matt Strassler run the numbers using our best measurements of the Higgs field, they get a sobering but reassuring timeline. The expected time for a bubble to appear somewhere in our entire observable universe is often calculated to be far, far longer than its current age. We're talking timescales so vast they dwarf all of cosmic history. 10 to the power of 100 years or more. Numbers so large they have no analogy in human experience. This is the good news. The math suggests our cosmic valley isn't just metastable but profoundly so. It could last for an epoch that makes the age of stars look like the blink of an eye. And yet, the key point remains in the silence after the calculation. The probability is not zero. It can never be zero. As long as quantum mechanics and the false vacuum are real, the chance exists. This introduces an element of eternal, cosmic uncertainty that science can't fully dismiss. It means that while we are almost certainly safe for timescales beyond comprehension, the absolute guarantee of safety is an illusion. Our universe carries within its fundamental fabric a tiny, unerasable line in the risk column. This isn't a call for alarm, it's a profound insight into the nature of our reality. We don't live in a clockwork universe of certainties. We live in a probabilistic one where even the most permanent-seeming structures, the laws of physics themselves, rest on a foundation of quiet chance. The odds are overwhelmingly in our favor, but they are not and can never be 100%. That uncertainty opens up a fifth mystery, one that looks outward. Has it already happened somewhere else? Our view of the cosmos is limited. We see the observable universe, a sphere centered on us, bounded by how far light has traveled in nearly 14 billion years. But the full cosmos, if inflation is right, is almost certainly much larger, unimaginably larger, maybe infinite, and in an infinite expanse the statistics shift. If a quantum bubble is possible here, and the universe beyond our horizon is eternal and infinite, then it isn't just possible elsewhere, it becomes inevitable. Not once, an infinite number of times, entire regions of space far beyond anything we could ever see, could have already undergone true vacuum decay. Vast domains of alien physics expanding at light speed might be spreading through the darkness right now, a cosmic patchwork stitched together from bubbles of different laws. Some bubbles might contain physics even more hostile to life than our worst predictions, barren voids. Others might, by pure chance, harbor laws more favorable for complexity than our own. It's a breathtaking thought. Our universe, with its life-allowing constants, might not be special. It might just be one stable bubble in a frothing meta-universe. This connects to a grander theory, eternal inflation. Picture a primordial, hyper-energetic state, a sea of inflating space. In that sea, random quantum fluctuations can cause pockets to drop out of the rapid expansion. To settle into lower energy states, each pocket becomes a separate universe, a bubble with its own random set of physical laws. Our Big Bang might have been just that. The moment our local bubble of stable, hospitable physics nucleated in an eternally inflating background. In this picture, the threat of vacuum decay transforms. It's no longer just a potential end for our local bubble. It becomes the ongoing engine of creation for an endless multiverse. New bubbles with new laws are constantly being born in the unobservable beyond. Some are stillborn, collapsing instantly, others expand, and within them perhaps give rise to their own stars, galaxies, and unknowable forms of existence. So the haunting question shifts. We look up at the static, silent night sky, but beyond the veil of the observable, the cosmic landscape might be unimaginably dynamic. A seething ocean of creation and dissolution. Our safe valley might be surrounded by mountains made of entirely different logic, and we are forever isolated. Adrift in our stable pocket, unable to see the storms that may rage just beyond the edge of all we will ever know. The cosmos might not be silent. It could be full of final messages. If a true vacuum bubble started somewhere, could it leave a trace? Could we see the end of physics coming? The answer is maybe, a haunting maybe. The first clue wouldn't be the bubble itself. That wall moves at light speed. You wouldn't see it until it arrived, but its birth or its passage through a galaxy might send a shockwave. A catastrophic change like that for a whole region of space should release energy. An unimaginable burst. Think of the domain wall, that sheet of pure energy plowing through a galaxy, converting stars and nebulae into new matter under new laws. That process wouldn't be clean. The violent rearrangement of forces could unleash radiation, gamma rays, X-rays, particles we have no name for. It could look like the most powerful gamma ray burst ever. But with a strange signature, isotropic, appearing across the sky from a single point, then vanishing as the source is erased. Another possibility. The sudden formation, the rapid expansion, would distort spacetime around it. This could generate gravitational waves, not the gentle chirp from colliding black holes, a sharp pulse, or a continuous, low-frequency hum as the wall sweeps through dust and dark matter. Our observatories are listening, LIGO future space detectors. They're tuned for collisions, not erasures, but an anomalous signal, one that doesn't match any known template, could be a clue. A ghostly echo, a law being rewritten a billion light-years away. The most profound clue might be in the oldest light, the cosmic microwave background. That faint glow from the Big Bang, a snapshot of the infant universe. If a true vacuum bubble formed in the distant past, far beyond our horizon, its passage could have left a scar. The immense energy of its domain wall could have imprinted a pattern, a strange, circular pattern, a sudden temperature discontinuity on that primordial canvas. Cosmologists map those minute fluctuations. They look for signatures of early physics, an anomalous pattern, a perfect circle of altered temperature that defies all the standard models. That would be a discovery, staggering and terrifying, evidence our universe is not pristine, that it may have been grazed by a region of alien physics. The hunt for that signature is the ultimate detective work, searching for a fingerprint of a suspect that could erase all other evidence. And here's the cruel irony. All these signals, the flash of radiation, the pulse of gravitational waves, the scar on the background, they travel at light speed, the same speed as the bubble wall. In the best case, the warning and the wall are separated only by the moment between the bubble's birth and its steady expansion. A thunderclap and the lightning arriving almost together. By the time our telescopes see an anomalous flash from a distant galaxy, the domain wall might already be on its journey. If the bubble started 1,000,000 light-years away, the warning and the catastrophe would be separated by a cosmic heartbeat. There is no early warning system for a light-speed erasure. The first proof our laws are not eternal could be the last piece of information our physics ever processes. That turns the search into something philosophical. We'd be hunting for a message that says, "This has happened," with the subtext, "It will happen here and soon." It's the knowledge that some truths, once discovered, offer no chance for response, only understanding, in the final moments before the rules of understanding themselves change forever. The expansion of the cosmos is accelerating. That's not just a fact, it might be a catalyst. This sixth mystery ties two puzzles together: dark energy and the stability of our vacuum. It could be a dangerous loop. We've known for decades the universe is expanding, and that expansion is speeding up. Something is pushing galaxies apart. A gentle, repulsive force, we call that dark energy. It acts like a property of empty space itself, a constant energy density, the cosmological constant. And this constant, this dark energy, might be connected to the vacuum energy we've been talking about. The Higgs field gives the vacuum its energy one way. Dark energy is another form, more mysterious. They're two sides of the same coin, or two different coins in the same purse. The question is whether they talk to each other. Could dark energy, as it becomes more dominant, actually lower the hill between our false vacuum and a deeper one? Think of that energy barrier again. The marble in the shallow dip. Now imagine the hillside itself is changing shape over billions of years. As dark energy becomes the main force stretching space, it might also be softening the landscape for quantum fields. Some models suggest this, that the cosmological constant isn't just a passive background. It could be an active participant in the vacuum's ultimate fate. If dark energy lowers the barrier, then the probability of quantum tunneling isn't fixed. It's a variable, a number that increases with time. The game of cosmic dice isn't played with fair dice. The dice are being weighted slowly, making the catastrophic roll more likely with each eon. That changes the threat from a static danger to an evolving one. In the far, far future, when the universe is a cold, dark, expanding void dominated by dark energy, the conditions for decay might not just be possible. They might become favorable. The final state wouldn't be an eternal freeze. It could be a trigger, a silent, empty cosmos stretched thin by dark energy, waiting to quantum tunnel into a new existence. The two greatest mysteries, what drives the acceleration and how stable is our reality, could be linked in a single equation, elegant and unsettling, where the answer to the first slowly, inevitably, unlocks the answer to the second. Maybe the universe isn't defenseless. There are ideas in theoretical physics, speculative ones, that suggest there could be safeguards, built-in features in the architecture that might prevent a true vacuum bubble from forming. It's not just a simple landscape anymore. It becomes a system of fortifications. The first idea is nested false vacua, so our universe isn't a single dip on a hillside. It's a valley inside a valley. The outer valley is one set of metastable conditions, but inside it there's a deeper, more stable gorge, and inside that gorge is the specific dip where we are. For a bubble to form, it wouldn't just tunnel through one energy barrier. it would have to go through a series of them, like breaking through multiple sealed doors to get to the core. Each barrier is a different kind of stability, a different layer of protection. The quantum fluctuation needed to trigger a full collapse would have to be catastrophically large. Coordinated across multiple fields at the same time, an event so statistically improbable it might never happen, even in an infinite cosmos. Then there's topological protection, where the geometry of the quantum field landscape itself creates natural defenses. Certain configurations might be wrapped or knotted in such a way that a simple tunnel to a lower state is topologically forbidden. The field would have to untangle itself in a specific, complex sequence to decay, a process so convoluted it's essentially locked in place. These ideas find a home in the string theory landscape, a framework that proposes a staggering number of possible vacuum states, maybe 10 to the 500 power or more. Each one corresponds to a different way for the extra dimensions of string theory to curl up. A different set of physical laws. In this vast catalog, our vacuum isn't just a random shallow dip. It might be a very special one, selected, perhaps by the Anthropic Principle, for its remarkable stability over cosmological timescales. Its specific configuration of fields and curled dimensions could have unique, self-reinforcing properties, like a precisely cut gemstone that locks into a setting. Our physics might be interlocked in a way that resists spontaneous unraveling. There could be fail-safes. If one field began to shift, feedback from others might pull it back. A kind of cosmic immune system, not designed by intelligence but by the mathematical necessity of lasting long enough for observers like us to arise. Of course, this is the frontier of speculation. We have no experimental evidence for string theory, let alone for these protective mechanisms. They're beautiful mathematical possibilities. A glimmer of hope written in equations we can't yet test, but they shift the perspective. They ask us to consider that the universe's apparent fragility might be an illusion. An illusion from looking at a single, simple model. The full architecture of reality could be far more robust, with layers of redundancy woven into the quantum fabric itself. It suggests the silence of the cosmos, the absence of any observed vacuum decay, might not be just good luck on a simple dice roll. It could be a signature of a deeply engineered stability. A universe that is, against all odds, built to last. We're left to wonder if the greatest cosmic mystery isn't how reality could end, but how it has managed to persist for so long. With such apparent grace in the face of its own fundamental instability. The seventh mystery is the information paradox. Quantum mechanics has a rule. Information can never be destroyed. It can be scrambled, hidden, encoded in complex ways, but it's never truly lost. The exact quantum state of a system, the complete description of every particle, contains information. And that information must be conserved. That principle is called unitarity. Think of it like this. If you knew the exact state of every atom in a burning book, you could run the equations backward. You could reconstruct the book from the smoke and ash. The information is still in there, just transformed. This rule is a cornerstone, yet the true vacuum bubble seems to shatter it. When the bubble wall passes, it doesn't just transform matter. It transforms the laws that govern how matter behaves. The old quantum states, the arrangement of particles that made up a galaxy, a planet, a thought, they're translated into a new system with a different rulebook. The old information, the code written in our physics, becomes gibberish in the new one. It's not like burning the book. It's like the alphabet itself has changed. The original text is now just a random sequence of squiggles with no meaning. From the perspective of our old universe, that information seems to have vanished. Poof, gone. This creates a paradox. Does the bubble violate a fundamental law of quantum mechanics? Or does the information somehow survive the transition? Physicists have wrestled with similar puzzles, most famously with black holes. The black hole information paradox asks what happens to information about matter that falls into a singularity. Does it get destroyed, or is it preserved on the event horizon? The true vacuum bubble is an even more extreme version. It's not a black hole eating information. It's the entire rulebook for information processing being retired. So where could the information go? One idea is that it gets imprinted onto the bubble wall itself. That domain wall of pure energy, expanding at light speed, might be more than just a boundary. It could be a cosmic hard drive, a holographic surface encoding in its energy structure, a complete description of everything it has erased. Another possibility is that the violent transition radiates the information away. In the moment of conversion, as stars and atoms are recast, a flash of radiation is emitted. Not just any radiation, but a carrier of the entire quantum state of the annihilated region. The information would be broadcast into the new vacuum like a final, indecipherable message. But who or what in that new reality could ever decode it? The most unsettling possibility is that unitarity simply doesn't apply here. That when the entire framework of physics changes, the old rules of information conservation break down with it. This would mean our current theories have a fundamental limit. They can describe a stable universe, but they cannot fully describe its total, absolute transformation. The bubble becomes a frontier, a place where the map of physics ends. Both the black hole paradox and the vacuum decay paradox point to the same gap in our understanding. They are edges where space-time and quantum logic seem to tear. Solving one might illuminate the other. For now, the paradox stands, a reminder that if the cosmos can erase its own laws, it might also erase the memory of what came before, leaving not just an empty universe but a forgotten one. The question here isn't just a scientific one, it's human. If everything we know is built on something that could just disappear, what does that mean? For our stories, for the things we make, for whatever we hope might remain, this idea, it isn't just in the math, it reaches into philosophy. It touches that old fear, the fear of being insignificant. That in the grand scheme, nothing we do matters, and a true vacuum bubble, that's the final argument for that. It says every monument, every memory, every act of kindness or creation, it could all just become noise. Cosmic static from a random event out in the void, our entire history erased not by time but by a change to time's own rules. It's a staggering thought. It can feel deeply unsettling, but there's another side to this. The fact we can even think about this ending, it's extraordinary. We exist in this sliver of cosmic time. A stable age, where the laws of physics allow for atoms, for stars, and for minds complex enough to see their own fragility. We've put together the story of the universe. From the first moments to the possible last ones, that self-awareness, it's a gift from our specific, stable physics, and it turns our potential erasure from just a catastrophe into a kind of paradox. We are the universe understanding its own temporary nature. That awareness, it changes our whole pursuit of science. Every telescope pointed up, every collider buried underground. Every equation on a board, it becomes part of a race against a clock that might not even exist in time. We're gathering knowledge about a reality that may not be permanent. Looking for truths that could one day be obsolete, but that doesn't make the search pointless. It makes it urgent. It makes it beautiful. This stability we have, this epoch that allows for life and curiosity, it isn't a given. It's a temporary sanctuary in a landscape of potential chaos, and seeing that, it doesn't have to make our lives feel smaller. It can clarify them. It shows the incredible preciousness of the here and now. Not just our personal lives, but this whole chapter of cosmic history, where questions can be asked, where answers can be sought. Our meaning, it doesn't come from demanding permanent cosmic relevance. It's forged in what we do with this fleeting, stable moment we have to learn, to create, to connect. these acts become our defiance against the silent probability. This is how we inscribe our story, however temporarily, onto the universe, not because it will last forever, but because right now, under these specific, miraculous laws, it can. The physics here has a name, a first-order phase transition. We see it in our world, but this is the cosmic version, water turning to steam. In a pot, the water heats. Bubbles form at tiny spots on the surface. They grow, they merge. The whole liquid boils away, becomes a new state. That's the transition. The universe decaying from a false vacuum to a true one is exactly that. But instead of water to steam, it's one set of physical laws becoming another, and the energy released isn't gentle heat. It's the latent energy of the cosmos suddenly set free. That latent heat is the eighth mystery. When the Higgs field tunnels down, it drops to a lower energy. That difference has to go somewhere. It doesn't vanish. It's dumped catastrophically into the bubble wall and the space around it. This energy fuels the wall's expansion. It's the engine. The domain wall isn't just a boundary. It's a tsunami front of released potential, a shock wave of cosmic power. The numbers are beyond us. The energy density could be billions of times greater than a star's core. A wall of that, even thinner than a proton, sweeping through space would be the most violent event, and that violence leaves a mark. Such a sudden, immense release wouldn't be clean. It would create things. As the wall moves, the forces at the boundary could rip particle pairs from the quantum foam. Not ordinary particles, exotic, heavy ones predicted but never seen. Or particles that only exist under the new laws. The bubble's birth could trigger a firestorm of creation, a shower of strange matter and radiation, heralding the new regime. A brief, brilliant flash of the old physics dying, giving birth to a physics unknown. This connects to our own deepest past. Cosmologists think our early universe underwent phase transitions. As it expanded and cooled, the fundamental forces may have frozen out from a unified state into the separate ones we know. Those early cosmic shifts would have been violent. They would have released gravitational waves, ripples in space-time. Our observatories are now searching for that primordial gravitational wave background. A whisper from the first moments. A true vacuum bubble today would be that same process, but in reverse. Not a cooling into order, but a catastrophic shift into a different order. And it would generate a gravitational wave signal of unimaginable strength. Not a whisper, a scream, a sharp, intense burst against the gentle hum of merging black holes. Understanding this energy changes the threat. It moves the bubble from a silent erasure to a process with violent, quantifiable physics. We can model the energy. Estimate the particle showers, predict the gravitational wave signature. It turns a philosophical dread into an observational puzzle. It gives us something to listen for. In the silent data of our gravitational wave detectors, or in an anomalous, all-sky flash of radiation, we might one day find the evidence, the storm of energy that announces not just an ending, but a violent, creative rebirth into a reality we can't visit and can't comprehend. The final act of our physics would be to broadcast the news of its own replacement, in a language of energy and waves that, for one last moment, we might still understand. The deepest clues about this erasure might come from the coldest places on Earth, labs where they get things almost to absolute zero. They're not building the end of the universe there. They're building its echo. They use clouds of atoms chilled down so far to simulate how a quantum bubble might begin. This is the world of Bose-Einstein condensates. Millions of atoms stop being separate. They merge into one quantum wave, a superfluid. In that state, you can create a false vacuum. You tune magnetic fields to trap the condensate in a metastable state. It's like a shallow dip in an artificial energy landscape. Then you watch and wait for the quantum tunnel. Just like in the cosmos, a random fluctuation can push a tiny part of the condensate into a lower energy state. A microscopic bubble of true vacuum forms and it expands. It races through the cloud. Scientists can track that growth with lasers. They measure its wall, its speed, its very beginning. These experiments from places like the University of Chicago or MIT are safe, contained looks at a principle. They validate the quantum math of false vacuum decay. They show the models predicting cosmic instability aren't just abstract equations. They describe a real process you can see. The lab bubble isn't rewriting physics. It's proving that such a rewrite is woven into quantum reality itself. Other analog systems give different views. Supercooled water kept liquid far below freezing is a classic metastable state. One vibration can trigger instant crystallization. The ice front spreads. It transforms the whole volume. That's a first-order phase transition in a beaker. Magnetic materials can be pushed into false vacuum states too. Their atomic spins get temporarily trapped in an alignment. Applying the right pulse can cause a domain wall, a boundary between magnetic orientations, to sweep through the material. Each of these lab analogs teaches us something about nucleation, about propagation speed, about the release of latent energy. They're small-scale rehearsals for a cosmic drama. By studying them, we aren't predicting doomsday. We're learning the universal language of change, how order shifts, how stability falls. The principles are the same, whether in a cloud of ultra-cold atoms or the quantum fields of deep space. This work turns a terrifying cosmic speculation into a rigorous branch of physics. It gives us data. It turns philosophy into measurement, and that offers a strange kind of comfort. We're not just passive observers of a potentially fragile cosmos. We're its students. Using the stable, local laws we have, we build models to understand the instability that might lie beneath them all. The lab becomes a sanctuary for understanding the unsanctified, a place where we can safely ask the universe's most dangerous question and listen for its answer in the quiet growth of a bubble no bigger than a speck of dust. Time could be rewritten inside that bubble. The way we experience time moving forward, it's not just some universal clock. It comes from physics, the second law of thermodynamics. The law of increasing entropy. The universe goes from order to disorder, from concentrated to spread out. Coffee cools down, a sand castle falls apart. Those changes create a direction, an arrow. We remember the past when the coffee was hot, the castle was whole. We move toward a future where everything is mixed, cooled, disordered. That arrow is woven into our consciousness, into the cosmos itself. But if the new vacuum changes the rules of thermodynamics, the arrow of time isn't a fundamental law like gravity. It's emergent, a trend that comes from the specific starting conditions of our universe, from the statistical behavior of particles. If the bubble has different constants, a different starting state, that trend could break. Or reverse, picture a universe where the default is maximum disorder, where the natural flow is from chaos to order. From our perspective, time there would run backward. A broken glass reassembling on the floor, leaping back to the table, light converging into stars instead of radiating away, memories forming of events that haven't happened yet. To someone inside that bubble, their experience would feel normal. Their past would be our future, their cause our effect. The bubble wall wouldn't just separate physical laws. It would separate two narratives flowing opposite ways. This isn't just science fiction. Physicists like Sean Carroll have looked at models where pockets of a multiverse could have reversed thermodynamic arrows. The math allows it. If our bubble of low entropy gave us a forward arrow, a bubble with a different entropy gradient could point the other way. The implications are staggering. The end of our universe wouldn't just create new space, new particles. It could create a new story, a plot that runs in reverse, where the climax from our view happens at the beginning, and the quiet beginning happens at the end. It reshapes the idea of cosmic history, our 14 billion-year march from a hot, dense, ordered state to a cold, dark, disordered one. That's our local story. It's not universal truth. In the grand meta-universe, other stories might unfold the opposite way, or in loops, or with no clear direction at all. The bubble becomes more than a physical threat. It's a narrative threat. It suggests the framework of history, cause and effect, memory and anticipation, our local conditions, temporary gifts from our specific vacuum state. If that state decays, the story ends, not with a final chapter, but with the entire concept of chapters being retired. It makes you wonder if the permanence we look for in legacy is an illusion built on a temporary arrow. And if the ultimate cosmic reset doesn't just change what exists, but the very direction existence is read, maybe the quantum bubble isn't just an eraser. It could be a seed that leads to a radical idea, borrowing from biology to explain the cosmos. Cosmic natural selection. Physicist Lee Smolin proposed it. In this view, the multiverse isn't a static landscape. It evolves. It has a Darwinian history and vacuum decay, black hole formation. These aren't endings. They're reproductive acts. Each one gives birth to a new universe, a child cosmos with physical constants slightly mutated from its parent. Our universe, with its stability, its abundance of stars and black holes, isn't an accident. It's a product of selection. Universes that are stable enough to last, fertile enough to produce many black holes, which then birth new universes. They come to dominate the multiverse population. So the terrifying quantum bubble transforms. It becomes a mechanism of cosmic reproduction. If our false vacuum decays, that new bubble of true vacuum isn't just an alien realm. It's a newborn universe with its own different laws. Its own potential for stars, black holes, maybe its own observers. The phenomenon that spells the absolute end for us becomes the absolute beginning for something else. This frames everything within a grand, cyclical narrative. Birth, death, evolution on a scale beyond imagination. Our cosmos lives, it produces offspring through its most violent events, and eventually it may die, making way for its descendants. It's a strangely biological perspective. The constants of nature aren't fixed by a first cause. They're tuned by a blind, iterative process across eons. The speed of light, the strength of gravity, these could be the cosmic equivalent of a giraffe's long neck or an eagle's sharp vision. Traits that enhance survival and reproduction in a competitive multiversal environment. This reframes our search for meaning. If our universe is part of a lineage, then its story isn't isolated. It's a chapter in a much longer saga. Our existence here, in this stable, life-allowing epoch, might be a necessary step in a cycle of cosmic generation. The very fragility that allows for a bubble to form also allows for something new to be born. It turns the existential threat into a note in a larger song of creation. Where endings are always inevitably new beginnings, our awareness of the cosmos could be part of its structure. This 10th mystery, it asks a startling thing. Could consciousness, the act of observation, actually play a role in keeping reality stable? It goes into speculative ground where quantum foundations meet the ultimate fate of everything. In quantum mechanics, particles exist in a haze of possibilities, a superposition of states until they're measured. Some interpretations, like the Copenhagen one, suggest the act of observation by a conscious entity is what forces the particle to choose. It collapses the wave function from probability into a single fact. That's the observer effect, but scaled up from the lab to the whole universe. If observation defines reality at the quantum level, then what does that mean for the vacuum, for the quantum fields underneath everything? Could a universe without any observers, without any conscious measurement, exist in a more fluid state? A more unstable state where the false vacuum is more likely to fluctuate, to tunnel, because no one is there to pin it down. It's a profound inversion. We usually think of consciousness as a fragile product of stable physics, but this idea flips it. Consciousness, through the simple act of looking, of measuring, might be a subtle reinforcing force. A gentle pressure holding the familiar world in place. Our collective observation, the sum of all conscious moments across the cosmos, could be a quiet participant in cosmic engineering. Not by design, but by the inherent rules of quantum reality, and that leads to a mind-bending possibility. The stability we enjoy, the long-lasting epoch that allows for stars and planets and life, might not be a happy accident. It could be, in part, a consequence of the life that arises within it, a self-reinforcing loop. Stable physics allows for observers, and those observers, through quantum observation, help maintain that stability. It's a cosmic version of the Anthropic Principle, but viewed through a quantum lens. Now, this is highly controversial. Many physicists reject giving consciousness any special role. They favor interpretations like decoherence, where interaction with the environment causes collapse, not a conscious mind. Yet the question remains, it's philosophically potent. It bridges the gap between microscopic quantum weirdness and the macroscopic fate of everything. It suggests the answer to why the universe has lasted so long might not be found only in equations of fields and energy, but also in the nature of perception itself. Which leaves us to wonder if the greatest threat to cosmic stability isn't a random quantum fluctuation, but a future silence, a distant era when the last star winks out and the last conscious mind ceases to observe. Would the universe, then untethered from measurement, become more volatile, more likely to slip into a new state? It's a poetic thought, a haunting one. That our presence, our curiosity, our very act of witnessing the night sky, might be a faint but essential thread in the fabric holding reality together. The universe has a future we can't really grasp, trillions of years out. This is the deep time that comes after the stars. The last stars, the red dwarfs, they've finally gone dark. They burned for 10 trillion years, now that's over. No new stars light up. The galaxy becomes a graveyard, just remnants, black holes, neutron stars. Cold white dwarfs, and between them this expanding sea of darkness. This is the era of decay. The universe is old, it's cold, and it's profoundly still. And in that stillness something might shift, the threat of the quantum bubble. It could change from a remote possibility into the likely final chapter. The reason is the quiet. Right now, our universe is noisy, energetic. Stars blast out radiation. Cosmic rays move through the void. There's the cosmic microwave background, this gentle warmth. That thermal noise, that background hum, it actually does something. It can suppress certain quantum effects. It's like trying to hear a whisper in a crowded room. The whisper is the tiny quantum fluctuation that could start a bubble. The crowd noise is all that thermal energy. It drowns the whisper out, but in the far future, the crowd leaves. The room goes silent. The universe approaches absolute zero. The thermal noise drops to almost nothing. In that ultimate quiet, the quantum whispers become clearer. The probability of a random, large enough fluctuation might not increase in an absolute sense, but the conditions get more pristine for one to succeed without interference. Some models suggest an even more direct link. As dark energy accelerates the expansion over these eons, stretching spacetime incredibly thin, it might also be reshaping the quantum landscape itself. The energy barrier protecting our false vacuum could slowly lower, like a hill being eroded by an endless wind. The marble of our universe rests in its dip, but the sides of that dip are slowly wearing down. After a googol of years, a 1 with 100 zeros, the hill might be so shallow that a quantum nudge becomes almost inevitable. The universe, in its extreme old age, becomes fragile. Ripe for change, this reframes the bubble. It's not a random bolt from the blue during a vibrant cosmic noon. It's the natural conclusion of a story that's run its course. The long stability that allowed for galaxies and life, that was a phase, a brilliant temporary chapter, but all phases end. The universe's final act may not be an eternal, frozen darkness. It may be a transition, a single, silent quantum event in the endless cold, rewriting the last page of the book into a language no one is left to read. It becomes the period at the end of the sentence of cosmic history, a transformation that's less a catastrophe and more a completion. The universe, after an almost endless lifespan of dynamic structure, finally settles into its true, final form. Even if that form is one where the concept of form no longer has any meaning, it's a poetic vision, a somber one. Our cosmos lives a long, fruitful life, and then, quietly, it changes into something else entirely. Black holes have this secret at their center, where gravity goes to infinity and physics as we know it just ends. That's the singularity, a point of infinite density where the curvature of spacetime itself breaks down. Our equations don't work there. It's pure quantum gravity, completely untamed, and in that chaos some see a potential for birth, not destruction but a new creation. So the question is whether the singularity could be the perfect seed for a true vacuum bubble. You have to consider the conditions. At the singularity, reality is stressed past any limit we can define. The quantum fields that fill everything are twisted and warped beyond imagination. In that environment, a stable vacuum, our false vacuum state, might not exist. The energy barriers that hold the Higgs field in its valley could be totally overwhelmed. It's like taking a balanced marble and putting it in a hurricane. The orderly landscape is gone, replaced by violent, random motion. In a place like that, a phase transition might not happen through a gentle quantum tunnel. It could be a catastrophic rupture. The field could be forced into a lower energy state. A bubble of true vacuum could form right at the singularity. This new region with new physics would start to grow, but it would begin its life trapped behind the event horizon, the point of no return. For a while, the bubble would be hidden, expanding inside the black hole's gravitational prison, feeding on the immense energy of the singularity itself, and that leads to a staggering idea. The black hole, known only for consuming, could transform. From within, it could give birth to an expanding region with new physical laws. As the bubble grows, it would eventually reach the event horizon and pass through it. At that moment, the black hole would stop being a feature of our universe. It would become the source point for a wave rewriting reality, a gateway, the ultimate destroyer becoming the ultimate creator. The bubble would expand into the wider cosmos at light speed, its wall coming from where the black hole once was. This idea brings together two big mysteries. The mystery of the singularity, where our physics ends, and the mystery of vacuum decay, where our physics could be replaced. It suggests the endpoints of stellar collapse might also be starting points. A black hole wouldn't just be a tomb. It could be a cosmic egg, incubating a new set of rules in its heart of darkness. This changes how we see these objects. If even one black hole underwent this transition, it would mean the end for our local physics, but in a multiversal sense, it would be a way for physics to propagate. Every black hole formation becomes a potential nucleation event for a new universe. Our cosmos, with billions of black holes, might be fertile ground for that. We look at these dark silhouettes not knowing if inside their hidden cores, an alien physics is already stirring, waiting to emerge and rewrite the sky. It turns the symbol of finality into a symbol of transition. Where the laws break down, new laws may begin. The line between science and science fiction can blur. And that's a good place to stop, to separate them. It's a reality check. On one side, there's peer-reviewed physics. On the other, narrative extrapolation. Both matter, but they're different. What we've been talking about, false vacuum decay, belongs to the first. It's a speculative but valid consequence of our best theories. The math of quantum field theory allows it. That framework predicted the Higgs boson. The idea our vacuum is metastable is discussed seriously in journals, at conferences. When scientists estimate the universe's lifetime using Higgs data, that's a real risk assessment, uncertain but real. This isn't fringe. It's exploring the logical boundaries of our models. It's the what if that comes straight from the equations, but almost everything after the bubble forms, that's extrapolation, the dramatic details, the new laws inside the bubble. A reversed arrow of time, information preserved on the domain wall. These are narrative explorations. They're what-if scenarios built on the first what-if. Guided by principles like information conservation or string theory concepts, but they aren't predictions. We have no equations for a true vacuum. By definition, its rules are ones we don't have and can't write. Any description of its interior is imagination, constrained only by the logic of different. That distinction matters. It's the difference between saying the equations allow this process and saying this is what the process would look like. The first is theoretical physics. The second is often philosophical or science-fictional narrative. Take the idea that no warning could outrun the bubble wall. That's a direct consequence of relativity, solid physics, but describing how the sky would change color as the wall hits the atmosphere, that's a narrative device. To make the consequence feel real, it's a plausible scenario based on light and matter, but it's an illustration, not a forecast. This balance is the scientific method. Imagination proposes a wild possibility, a universe on unstable ground. Rigor tests it against math and observation, pairs it back to its logical skeleton. What's left is a possibility, an unsettling one. Our cosmos might not be permanent. The rest, the tapestry of what that end feels like or what comes after, that's where story takes over. It's how we grapple with the scale of the ideas. Both parts are essential. The theory gives the concept weight. The narrative gives it meaning. Knowing where one ends and the other begins doesn't reduce the wonder. It deepens our appreciation for the careful, disciplined imagination that drives discovery. The holographic principle kind of inverts things. It says the three-dimensional world we see, the space, the stars, might not be the base layer. It could be a projection, like a hologram. The real, full description of everything might be written on a far-off, two-dimensional surface. Think of a Blu-ray disc. The data on it creates a three-dimensional movie. Our universe could be that movie, a detailed illusion generated from flat data at the edge of space. So that's the 12th mystery. If reality is a hologram, what occurs when a true vacuum bubble appears? That event we called a wall moving through space, it changes. It's not a physical wave in 3 dimensions anymore. It becomes something else, a corruption in the source code, a spreading glitch in the cosmic data. Picture the universe's underlying structure as a huge, 2-dimensional grid. Each point on that grid holds data that projects our 3-dimensional world's laws and contents. In a stable universe, that data is coherent. It describes the Higgs field in its false vacuum state. It defines the constants. Then a quantum bubble nucleates. From the holographic view, this isn't a sphere growing in the projection. It's a local error in the source code. A patch of data on that 2-dimensional boundary flips. It now describes a different vacuum state with different laws. That corrupted patch is the seed. And because information on the boundary is connected, the error starts to spread. Adjacent data points get overwritten. The glitch propagates. In our projected 3-dimensional universe, we see this as the bubble wall. That domain wall moving at light speed is just the 3-dimensional manifestation of a 2-dimensional data corruption spreading across the cosmic hard drive. This reframes the threat in a modern, unsettling way. The end of physics isn't a force of nature overwhelming matter. It's a virus in the operating system. A rewrite of the universe's foundational programming language. The holographic principle comes from studying black holes and quantum gravity. It started with a paradox. The information falling into a black hole seems tied to the area of its event horizon, not the volume inside. That hinted the true degrees of freedom in a region of space might be painted on its boundary, not contained within. Applying this to vacuum decay gives a radically different lens. The bubble's interior, with its alien physics, isn't a place you could visit. It's a region of the hologram generated by a completely different set of instructions. The domain wall is the projection of the moving line between two incompatible data sets. This perspective could solve, or at least reframe, the information paradox from earlier. If all information is stored on the boundary, then when the bubble passes through a star, the information about that star isn't destroyed in the three-dimensional projection. It's translated. The data on the two-dimensional surface is updated. It now describes whatever new configuration of particles exists under the new laws. The story is preserved but written in a new, alien alphabet on the same fundamental surface. From our doomed three-dimensional viewpoint, it feels like annihilation. From the boundary's perspective, it's an edit. This connects the quantum bubble to the cutting-edge quest for a theory of quantum gravity. The holographic principle is a cornerstone of ideas like the AD/CFT correspondence, which links a theory of gravity in a volume to a quantum field theory on its boundary. In that framework, vacuum decay in the volume corresponds to a specific, catastrophic phase transition in the boundary theory, a sudden rearrangement of its quantum state. We're left with a profound shift. The fragility of the cosmos might not be about space and energy fields. It might be about information integrity. The stability we rely on is the stability of a cosmic program that's been running flawlessly for nearly 14 billion years. But all programs can crash, all data can be corrupted. The holographic view doesn't make the bubble less real. It makes its nature more fundamental. It suggests that if we ever saw the onset of decay, we wouldn't just be seeing the end of our physics. We'd be glimpsing for a terrifying instant the projector behind the screen and watching as its code was overwritten, line by inexorable line, by something utterly unknown. There's a danger that stands alone. When we list global catastrophic risks, asteroid impacts, supervolcanoes, pandemics, nuclear war, those are immense threats. But they share things in common. They're physical events. They follow known laws. They are, in principle, detectable. You can track a large asteroid years ahead. You can model how a pandemic spreads. There's a before, a during, maybe an after. A chance to respond, to mitigate, to survive. The quantum bubble erases every one of those categories. It's not a disaster inside our universe. It's a change to the universe itself. Its properties define a new class of existential risk. First, it's fundamentally undetectable until it arrives. No telescope, no sensor, no early warning system can see past the light speed wall. Second, it's utterly unstoppable. There's no technology, no bunker, no distant colony that could survive a rewrite of the strong nuclear force. Survival isn't a question of resilience or distance. It becomes a logical impossibility under the new rules. Third, its effect is total. It doesn't just end human civilization or planetary life. It ends the very framework that allowed for civilization or life to be conceived. It targets the operating system, not any single program running on it. That introduces a philosophical shift. Most catastrophic risks come with agency. Human error, natural cycles, cosmic chance we might deflect. They come with a narrative of cause, sometimes blame. The quantum bubble carries none of that. There's no one to blame, no policy failure, no neglected telescope, no hubris to point to. It's a random number in a cosmic lottery, drawn from the quantum foam. It offers no possibility of prevention. We can't reinforce the Higgs field. We can't put up a shield against a change in the law of gravity. Our agency, our human capacity for problem solving, hits a fundamental limit. A wall not in space, but in the logic of what's possible. That forces a confrontation with a unique kind of probability. The math says the chance in any given century is so small it's effectively zero for planning. Yet it's definitively, mathematically, not zero. How does a rational mind or a society process that? We're excellent at assessing clear and present dangers. We build levees for 100-year floods. We scan the skies for asteroids. We prepare for risks with precedent. But how do you prepare for a threat with no precedent, no warning, and no possible action? You can't stockpile supplies for it. You can't draft an evacuation plan. The only preparation it allows is internal, philosophical. It becomes a mirror, reflecting our relationship with absolute uncertainty. That moves the discussion from physics into risk philosophy and meaning. Living in the shadow of such a threat isn't about daily fear. That would be irrational given the timescales. It's about recognizing a foundational truth of our condition. We exist in a temporary sanctuary of stable physics. That sanctuary's lease is incredibly long, but it's not eternal. This knowledge can be framed in two ways. One is a source of existential dread, highlighting the ultimate fragility of all achievement. The other, perhaps, is a source of profound clarity. It strips away the illusion of permanence we often project onto our civilizations, our monuments, even our planet. It tells us the meaning of what we do can't be anchored in lasting forever, because forever isn't on offer in this universe. Instead, meaning must be built in the quality of the temporary, in the connections we make, the beauty we create, the understanding we gather during this stable epoch. The cosmic gamble doesn't make our endeavors pointless. It frames them as precious precisely because they're not guaranteed. Every act of curiosity, from a child looking at the stars to a physicist plotting an equation, becomes a celebration of this rare, stable moment. It's how a species living on borrowed cosmic time chooses to spend its day, not in paralyzed worry about the loan's eventual due date, but in the vibrant, urgent activity that the loan makes possible. The quantum bubble, as a category of risk, ultimately asks us not what we would do to survive it, but how we choose to live in light of its remote, silent possibility. Our beginning might be a story about a bubble. We think of the Big Bang as the start of everything, but maybe it wasn't the absolute start. Maybe it was a transition. Like water freezing, this 13th mystery looks back to the idea that our universe came from the decay of something else, that our Big Bang was a bubble forming in a parent universe. Think of the false vacuum, a metastable state that can tunnel into a lower energy, more stable state. We've been thinking of that as our future, but it could be our past. The heat and density of the Big Bang could have been the energy released when a bubble of true vacuum, our vacuum, formed in a sea of false vacuum. Our entire cosmos, all the space and time we know, could be inside that bubble. Expanding and cooling, forming structure from that initial release of latent heat. This is the core of eternal inflation. It proposes a primordial, hyper-energetic state, an inflating false vacuum that exists forever. In that seething, expanding sea, random quantum fluctuations cause pockets to drop out of the rapid inflation. These pockets tunnel to lower energy. Each one becomes a separate universe, a bubble with its own random laws. Our universe, with its specific constants that allow for atoms and life, is just one of these bubbles, one stable valley in an endless cosmic landscape. If this is true, it puts our entire history in a new context. The 14-billion-year story of galaxies and stars and life is not the story of the universe. It's the story of our universe, our local bubble, a single chapter in an infinite, branching multiverse. The cosmic microwave background, that ancient afterglow, might not be the echo of the absolute beginning. It might be the thermal signature of our bubble's violent birth. This reframes the threat of our own vacuum decay. It changes a potential ending from a final erasure into a link in a chain. If our bubble decays, giving rise to a new region of true vacuum, that event wouldn't be an ultimate end. It would be cosmic reproduction. Our universe would give birth to a child universe with different laws. In this view, endings are also beginnings. A bubble wall isn't just a wave of erasure. It's a wave of genesis. The domain wall that would spell our end becomes the birth canal for a new reality. This introduces a dizzying sense of scale. Our observable universe, vast beyond comprehension, is just the interior of one bubble. Beyond our cosmic horizon, in the parent vacuum, countless other bubbles may exist. Other universes with physics alien to our own. Some may collapse instantly. Others may be vast and long-lived, hosting their own forms of complexity. We are forever isolated within our bubble's wall, unable to see this grander cosmic ecology. The mystery of what came before our bubble is untestable from within. We are inside and its walls are beyond our reach, but the idea offers a narrative. It suggests the stability we enjoy, the laws we've decoded, are not a miraculous, one-time accident. They might be a common outcome in a process that has been running for eternity. Our existence here is not a singular event, but a probable one in an endless cycle. This perspective can be humbling and strangely comforting. It removes us from the center of the cosmic story, yet weaves us into a tapestry of grandeur. The potential demise of our local physics is no longer a meaningless deletion. It becomes part of a deeper rhythm, a rhythm where every ending holds the seed of a new beginning, written in a language of quantum fields we are only beginning to understand. That elegant, terrifying probability comes from a specific shape, a mathematical shape. It describes the most likely way for a bubble to form. Physicists gave it a name. Sidney Coleman and Frank de Lucia, they called it the Instanton. It sounds like a particle, but it isn't. It's a solution, a precise mathematical description of the quantum tunnel itself. The blueprint for cosmic decay. To see it, you have to shift your view of time. In our world, time flows forward, 1 second after another. That's real time. But in the quantum equations for tunneling, there's a trick, a mathematical tool. You switch to imaginary time. That's a technical term. It doesn't mean time you make up. It means treating time mathematically like a fourth dimension of space. In this imaginary time landscape, the energy barrier isn't a hill to climb over. It becomes a mountain pass to go through. The Instanton is the path through that pass. It's the most probable route the quantum field takes from one valley to the other. The path of least resistance through the mountain, the route that needs the smallest, most probable quantum fluctuation to start the whole process. This path isn't through space. It's through spacetime. The Instanton describes a tiny, spherical region of true vacuum popping into existence, and it tells us exactly how. A helpful visual is a soap film. You dip a wire loop into soapy water, and the film that forms stretches across the loop. It finds the surface with the smallest possible area, a minimal surface. The Instanton is like that, but in 4 dimensions, 3 of space and 1 of imaginary time. It finds the shape of the bubble nucleation that requires the least energy to happen. This mathematical minimalism explains 2 things. First, why the bubble is spherical. A sphere has the smallest surface area for a given volume. In the quantum tunneling process, minimizing the bubble's surface area at its birth minimizes the energy cost of creating the wall. So nature, following the path of least action, chooses a sphere. It's the most efficient shape for a new universe to be born. Second, the Instanton shows why the bubble, once formed, must expand. The equations show the interior of this spherical region is in a lower energy state. The outside is in a higher energy state that creates a pressure difference. Like a balloon with higher pressure inside, it has to grow. The Instanton gives the initial push, and the energy landscape does the rest, sending the wall rushing outward at light speed. From this elegant math, physicists get the actual probability. The equations give a number, a staggeringly small number, the chance per cubic centimeter per second. Then they multiply that by the vast volume of the observable universe and by its immense age. That's how we get those cosmic timelines, 10 to the power of 100 years or more. The Instanton is the heart of it, a beautiful, abstract shape in an imaginary time landscape. It tells us our cosmos might not be forever. It grounds a vision of total transformation not in speculation, but in the cold, clean logic of mathematics. It turns an apocalyptic what-if into a calculated risk, written in the most fundamental language we know. The equations don't care about our fears, they just map the terrain, showing us the hidden tunnel that has always been there, waiting in the numbers. The equations we have, they're incomplete. They show potential instability, but they can't give a final verdict. That authority belongs to a theory we don't have yet. The 14th mystery asks what quantum gravity would say about the bubble. Our two great pillars of physics, quantum mechanics and general relativity, they describe the cosmos with stunning accuracy. But they refuse to speak to each other at the most extreme scales. At a black hole singularity, or in the first moments of the Big Bang, their combined predictions yield nonsense. Infinite values, a mathematical breakdown, that's the frontier of quantum gravity, and it's exactly the realm where a true vacuum bubble would be born. The nucleation event happens at a scale smaller than an atom, in a region of unimaginable energy density, the Planck scale. At that level, the smooth fabric of spacetime from general relativity is thought to dissolve into a quantum foam, a seething, probabilistic froth where concepts of before and after might lose meaning. Our current description of vacuum decay uses quantum field theory, which treats spacetime as a fixed stage. But if the stage itself is quantum and fluctuating at the moment of nucleation, the entire calculation changes. The hill between valleys, the tunnel through it, these are metaphors built on classical geometry. What if the hill isn't a static shape, but a vibrating, probabilistic entity? This is where candidates for a theory of quantum gravity enter. String theory, for instance, proposes the fundamental entities aren't point-like particles, but tiny, vibrating strings. In its framework, our vacuum state corresponds to a specific way the extra dimensions are curled up. A transition to a true vacuum would be a catastrophic rearrangement of that geometry. Some configurations in string theory are believed to be absolutely stable, protected by topological features that make decay impossible. If our universe corresponds to such a configuration, the quantum bubble isn't just unlikely, it's forbidden by the deeper architecture of reality. The instability suggested by the Higgs mass measurement would then be an illusion, a mirage from our incomplete view. Loop quantum gravity, another approach, quantizes spacetime itself. It suggests a discrete, granular structure at the Planck scale. This granularity could act as a stabilizing lattice. Imagine trying to form a perfect soap bubble on a rough, textured surface. The film might not sustain the perfect, minimal shape needed to nucleate and grow. The quantum graininess of space could prevent the Instanton, that perfect tunneling path, from ever forming. In this view, the cosmos isn't a smooth landscape, but a complex weave, and that weave may have no loose threads for reality to unravel. Yet the opposite is also plausible. Quantum gravity might not be a guardian, it could be a catalyst. The violent fluctuations of spacetime at the Planck scale could provide the ultimate energy source for nucleation. They might create shortcuts or entirely new pathways for decay that our current equations can't see. If spacetime is a quantum foam, It might be constantly bubbling with potential transitions, most of which instantly collapse. But one in all of eternity might succeed. The search for a theory of quantum gravity is often framed as a quest to understand the origins of the universe or the hearts of black holes. But it's also a search for the cosmic rulebook on stability itself. It seeks to answer whether the quiet order we experience is the final word, or just a temporary eddy in a more fundamental chaos. This mystery, then, isn't a passive speculation. It's a driving engine for fundamental physics. The haunting possibility of vacuum decay provides a concrete, existential stake in the abstract pursuit of unification. It transforms the quest from a purely intellectual exercise into a hunt for the ultimate safety manual of the cosmos. Until we have that theory, the bubble remains in a quantum superposition of possibility. Both a specter and a phantom, its reality suspended by our own ignorance, we're left with a profound uncertainty, not about the details of our end, but about whether the very concept of an end is written into the deepest laws, or if it's just a shadow cast by the limits of our light. Long before quantum fields, people told stories about the world ending. These weren't stories about quiet decay. They were about fire and ice, gods and monsters. The Norse had Ragnarök, a final battle where the world tree Yggdrasil shakes, the sun gets swallowed, and the earth sinks into the sea, and then it rises again. Green and fertile, in Hindu cosmology, time moves in these vast cycles, kalpas. Each one is a day in the life of the creator god, Brahma, and each kalpa ends in a dissolution. A pralaya, the universe is withdrawn into its source, a period of rest, then the cycle starts again. These aren't stories about random chance, they're narratives of order. A destined cleansing, often a necessary one, that makes way for renewal. The cosmic bubble theory, it resonates with that ancient rhythm. It replaces gods with quantum fields. Replaces destiny with probability, but the core pattern echoes stability, dissolution, and the potential for rebirth from a transformed state. Our oldest myths and our newest physics, they're both wrestling with the same haunting question. Is the world we know a permanent home, or is it a temporary shelter? This pattern extends into modern storytelling. The silent apocalypse finds new forms. In novels and films, a physics-ending event gets called a vacuum metastability event or a reality collapse. These stories try to visualize the unvisualizable. They show scientists staring at data, realizing the universe has a fatal flaw, and grappling with the helplessness that follows. There's no villain to defeat, no asteroid to deflect. The conflict becomes internal. A struggle for meaning in the face of a meaningless end. These narratives serve a crucial function. They translate cold, abstract probability into human-scale drama. They let us emotionally rehearse an idea that's otherwise too vast to hold in our minds. Too impersonal. By giving the quantum bubble a story, even a fictional one, we make it something we can process, something we can discuss, and ultimately, integrate into our understanding of the cosmos. This cultural lens is more than a coping mechanism. It reveals something fundamental about us, the fear of cosmic dissolution, of the rules themselves being revoked. That's a deep-seated part of our psychological landscape. For millennia, we've looked at the stars and wondered if they're eternal. Our myths answered with cycles of destruction. Our science now answers with metastability and quantum chance. Both are attempts to map the boundaries of existence, to find a story that makes the potential for an end comprehensible. They connect the personal to the cosmic. The anxiety we might feel about our own mortality finds a grand, mirrored reflection in the potential mortality of the very laws that govern reality. Seeing the quantum bubble through this storied history, it doesn't diminish the science. It enriches our relationship with it. It places a cutting-edge theoretical threat within a timeless human conversation. A conversation about fragility, impermanence, and legacy. It reminds us that the equations of quantum field theory are, in their own way, a new kind of mythology. A powerful set of stories we tell to explain the deepest workings of the world, and like the old myths, they shape how we see our place in the cosmos. Not as passive inhabitants of a fixed stage, but as conscious witnesses within a narrative that's still being written, on a parchment that itself may not be permanent. This connection between the oldest stories and the newest theories, it suggests that our quest to understand the universe's end is perhaps a fundamental part of understanding what it means to be here at all. A digital universe has its own fragility. If our cosmos isn't a fundamental reality, but a simulation running on some unfathomable computer, then the laws of physics aren't laws. They're parameters, variables in a cosmic program, the quantum fields, the constants, spacetime itself. They become lines of code, and code can contain bugs. Or it can have built-in termination sequences. This is the 15th mystery. It asks if the quantum bubble, that eraser of physics, might be understood not as a natural process, but as a digital event. In a simulated reality, vacuum decay could be one of two things: a catastrophic glitch or a deliberate feature. Think of a sophisticated video game. The world has consistent rules. Gravity works a certain way. Objects have mass, but sometimes a player finds a flaw, a sequence of actions the programmers didn't anticipate. It causes the game to freeze, or it corrupts the save file, rendering the entire world unplayable. The data becomes gibberish. Now scale that up to a universe. The Higgs field in its false vacuum state is a delicate variable in the cosmic code. A quantum fluctuation large enough to trigger tunneling might be that unanticipated sequence. A random bit flip in the memory of the universe simulating computer. It overwrites a critical value. The new value defines a different vacuum, and because the simulation is coherent, one piece of code referencing another, the corruption spreads. The bubble wall is the visualization of that corrupted data propagating through the system. From the inside, it looks like a change in the laws of nature. From the outside, in the realm running the simulation, it might look like a critical error log, a cascading failure, the ultimate blue screen of death for a reality. But there's another possibility. What if it's not a bug? What if it's a cleanup routine? Even the most powerful computer would have finite resources. If our universe is a simulation, it's consuming processing power and memory. Perhaps when a region of the simulation becomes too complex or too energetically expensive to maintain, the system has a protocol. A way to reclaim those resources, to reset that sector back to a baseline, zero-energy state, a true vacuum. The bubble would be that protocol in action. A wave of simplification sweeping through the simulated cosmos, turning complex structures into a blank, low-energy slate. Efficient, cold, logical. It wouldn't be malice, it would be garbage collection on a cosmic scale. Our stars, our galaxies, our existence might be seen as temporary data patterns, to be terminated when the system needs to free up space for new calculations. This perspective reframes the threat in a language we understand: information technology. The domain wall is no longer a sheet of energy. It's a firewall between operational code and corrupted or reclaimed data. The information paradox changes its nature. In a simulation, information isn't necessarily conserved. It can be deleted. A file can be erased from a hard drive. If our universe is such a file, then the bubble represents the moment the delete command is executed. Permanently, this connects to modern philosophical thought experiments like those from Nick Bostrom. If advanced civilizations could run ancestor simulations, we might be in one. And in any complex simulation, errors or scheduled maintenance are inevitable. The silence of the cosmos, the absence of obvious glitches, could be a sign of a robust simulation. Or it could mean the reset protocol hasn't been triggered in our local sector yet. We're left with a reframing. the end of physics would not be a natural disaster. It would be a system update or a crash, and we, as conscious patterns within the simulation, would have no more warning than a character in a video game has when the player pulls the plug. Our quest for cosmic meaning becomes a search for the user manual of a reality we can never see outside of. It suggests the deepest security of our existence rests not on the stability of quantum fields, but on the flawless execution of code in a realm forever beyond our reach. The dice have rolled in our favor for a long time, over 13 billion years, that's the fact. All the theories about instability, about decay, they're out there. But the universe has stayed coherent, stable, long enough for galaxies to form, for planets to be forged, for minds to emerge that can think about their own fragility. This epoch we're in, it doesn't feel random, it feels tuned, because the numbers, the constants that run reality, they're balanced on a knife's edge, gravity. Change its strength just a fraction, and stars either never light up or they burn out in a flash. The strong nuclear force, alter it slightly, and atomic nuclei can't hold together. The cosmological constant, tweak it, and the universe either collapses back on itself instantly or expands so fast nothing ever forms. This precise calibration, this fine-tuning, it's one of the deepest puzzles. It forces a question: why is the universe so hospitable to the complexity that leads to us? One answer is the Anthropic Principle. It's a logical filter. We can only find ourselves in a universe capable of sustaining observers. If there's a multiverse, infinite possibilities, where every set of physical constants exists somewhere, then it's no surprise we're in one of the rare, stable bubbles. A bubble where the laws allow for stars, planets, life. Our presence here is the evidence. It's the ultimate selection bias. We aren't observing a random universe. We're observing the only kind of universe we could possibly be in. To ask the question, this doesn't explain why the multiverse exists or why any laws are possible at all. But it reframes our stability from a miraculous accident into a statistical necessity. Of course, we see fine-tuning. We couldn't be here to see anything else. This principle changes how we see the quantum bubble. The threat is real. The probability isn't zero. But the fact that we are here now in a cosmos full of structure, that tells us something about the timeline. It suggests the metastable state we're in isn't fleeting. It's robust, lasting for cosmological epochs, long enough to nurture stellar evolution, biological complexity. We exist in a privileged chapter, a long, stable interval in what might be a much longer, more chaotic story of the multiverse. It's a chapter we're uniquely equipped to read. Our intelligence, our curiosity, our science, they aren't accidents separate from the cosmos. They're products of its specific, stable laws. We are the universe becoming aware of itself. And in doing that, beginning to question the very foundations of its own existence. This moment of awareness, this ability to hold the concept of our own potential erasure, it might be the most remarkable feature of this fine-tuned epoch. It doesn't guarantee our future safety. The dice are still rolling, but it tells us the present, this now we inhabit, is a rare island, an island of order in a sea of probabilistic chaos. An island we've been given, against all odds, the tools to map, to cherish, to understand, even as we look out at the dark waters that may one day inevitably rise. We started with a quantum field, just a tiny shiver, and we ended with the fate of everything, a thread of possibility connecting our reality to a deep, silent instability. The laws we think are absolute might just be local customs. A random event with no cause could rewrite the cosmic rulebook, our entire history, balanced on a foundation of temporary order. This pushes against the boundaries of science. It brushes against philosophy. What meaning do we find in a cosmos that carries the seed of its own transformation? The probability is so small, a number with more zeros than stars in the sky, but its existence isn't a prophecy of doom. It's an invitation to wonder. It forces our gaze upward with a new humility, a new clarity. The stable epoch we live in, this sliver of cosmic time where stars shine and minds can ponder their origins, it's not a given. It's a gift, a temporary sanctuary of physics that allows for beauty, for complexity, for the human drive to understand. Let that understanding settle. Not as a cold fear, but as a warm appreciation. Every time we look at the night sky, we're witnessing a miracle of stability in progress. Every question we ask about the universe celebrates the very laws that make questioning possible. This cosmic what-if reframes our place. We're not just passengers in a clockwork universe, we're conscious participants in a grand, dynamic, uncertain narrative. Our task isn't to live in dread of a remote ending. It's to fully inhabit the astonishing chapter we're in, to learn, to create, to connect, using the stable laws we have while we have them.